if you do not go to school, you will not be successful. Some people cannot go to school and they will still be what? Successful. But the chances is very what? Slim. And even if you become successful, you will now be employing those that went to school to help you to count your money.
Apart from that, they will use number to change.
They will use number to steal money. Because they went to school and you did not go to school. So if they bring contract now, they say this is where you will sign. The contract say, this contract is not good for you because you cannot read, you don't know what it means. You go and sign it because you will not go to school. So this morning we are going to talk about radioactivity. We have done it just under radioactive decay. We are going to be trashing it today. Just under radioactive decay, we are going to be trashing it today. If there's enough time, we may enter transmutation. So, who is the father of radioactivity, if I may ask? Who is the father? A French scientist known as who? Henri Becquerel, isn't it? So, what did Henri Becquerel do in his experiments to discover radioactivity? Don't write to, just listen. This is the introduction to it. When I write, you write, don't worry. Henri Becquerel did a very good thing. He discovered that there are some elements present on Earth that exhibit some special characteristics. So in his experiment, he took radon and then he placed radon into a lead block. And then he observed that when he put radon and passed it through a magnetic field, that 3 particles were emitted, and those particles were called the alpha particle, the beta particle, and the gamma particle. What he observed in this experiment was that the alpha particle were deflected to the negative, or rather to the south pole of the magnet, while the beta particles were deflected to the right, that's to the north pole of the what? Of the magnet. But the very stubborn particle called the gamma particle had no deflection. How did he observe these deflections? He put a photographic plate in front of what? The radioactive material. He didn't stop there. He said, okay, I want to still check the observation again. If I can put this radioactive material, thorium, across an electric field. So when he did that across the electric field, he also discovered that the alpha particles were deflected to the left, to the negative charges. And this is only true because we learn that law of what? Attraction. A positive charge will only be deflected to what? To meet a negative charge, isn't it? So, but for the beta particles, they were deflected to where? To the right. They were negative, so they had to go and meet what? The positive electric charges. But still yet, gamma particles were not what? Deflected. They have no charge. They are neutral. So Henri Becquerel discovered this. Who can tell me the year he discovered this? 18 what? Have you been born by then? Okay, our uncle was born by then. So this discovery opened up a new avenue for radioactivity studies to be made. So in our quest for learning today, we are going to look at the properties of those particles that were emitted and how it can affect radioactive elements. So first, let's go and put the definition of radioactivity. Usually this is not my handwriting, but I got a complaint online that they did not see my handwriting. Can I continue? Can I continue? Okay. Hello. So on the board, the definition of radioactivity is there. The founder, Henry Becquerel, and the meaning of the word radioactive elements is also on the board. So the type of radiations that were produced during this experiment is what we have drawn as alpha, beta, and gamma particles produced when a radium sample was what? Was observed on a photographic what? Plate. It was put across a magnetic field. Can we see the magnetic field in between the north and south what pole? So there's a uniform magnetic field here. Despite the fact that it was passed across it, alpha particles were what? Deflected to the south, while the beta particles were deflected to the north, and the gamma particles went straight ahead to hit the what? Photographic plate. No deflection was what? Was observed. So for the gamma particles, no deflection was observed. So the same was done, but this time around it was passed through an electric field where we have negative and positive charges. The same observation was made. So at this point, alpha particles still deflected to meet what? The negative charge of the electric field, and beta particles were also deflected to meet what? The positive charge. So the direction of deflection actually shows us one of the characteristics of each of these particles. One, you can see that alpha particles are positively charged particles. Why? Because they are being deflected to where? To the negatively charged plates. But beta particles are what? Negatively charged particles. Look at them being deflected to where? The positive plates. So the types of radiation that were being produced were just three. One is the alpha particle, the other one was the beta particle, and the last one was the gamma rays. So what do we want to know now? We want to know their characteristics. I'm going to be drawing a table for you later on to show the characteristics of these three particles that were what? Produced during radioactivity. So are you done? I want to clean. Are you done? Are you done? Now, aside from the experiments carried out by this Henry Becquerel, are there other means that we can detect radioactivity in some elements? Yes, there are. In fact, JAMB will ask you, what are other means or other methods of detecting radioactivity? This was just an experiment, the founder of this. Have you heard of, does anybody want to say other means? How can you detect or observe radioactivity? Any other means? You want to say something? Come again. Use of UV light? No. That's under light. That's under spectrum. Any other way of detecting radioactivity? Okay, have you heard of Geiger-Müller counter? That was a German scientist that also worked on radioactivity. He made a counter in which a radioactive element, when placed in it, will also what? Show alpha, beta, and gamma what? Particles. Have you also heard of the electron cloud chamber? That's another means to detect what? Radioactivity. So it might come out in OBJ. Other ways in which radioactivity can be what? Detected. So but now I want to know the characteristics of these three particles that were emitted, the alpha particle, the gamma particle, and just from this diagram alone, we have observed that the alpha particle is positively what? Charged, while the beta particle is what? Negatively charged. Can you see that? While the gamma particle has no charge at all, it is what? Neutral. But do they have any other properties? Yes. So I'm going to draw this table. This table will show the other properties that they do have. See the problem we have now. Now that there is fan, they will be sleeping. So can I clean now? Can I clean? Okay. So let's have the table. The table helps us to know the what? The features or of those particles or their characteristics. So these are the properties they are given to us in the table. We have for radiation, we have the nature of those properties. We have the velocity and the charge. We have the mass. And then we have what? The effect of magnetic field. Effects of magnetic field on that particle. Then also we have the ionization power. And then finally we have what? Penetration power. So the first particle there is what? Alpha particle. Followed by what? Your alpha particle is denoted like this. Then we have the beta particle, denoted by this. And then we have what? The gamma particle or gamma rays, as the case may be. So, most times an alpha particle we said is positively charged, and the characteristics of an alpha particle is just a helium particle, He 4 and 2 is positively charged. This is called a helium nuclei. Helium nuclei. It has a velocity of 0.15 to 0.21 times 10 raised to power 8 meter per second. We have plus 2e times 10 so for the charge raised to power minus 19 coulombs. Then for the mass, 6.65 times 10 raised to power minus 27 kilogram. We use the word alpha particles are relatively massive. The reason for using relatively is because we are comparing it to beta and gamma rays. So what are the effects of alpha particle under a magnetic field? Just as it has been seen in the diagram, alpha particles are deflected to the south pole, isn't it? Slight deflection. Slight deflection towards the south pole. What about the ionization power? It has heavy ionization energy. Penetration power, very little. Very little or no penetration power. In fact, alpha particles can be stopped by a piece of paper. So what about the beta particles? What's their nature? So beta particles, they are negative in nature, isn't it? But in nature, they are found to be what? To be electrons, high energy electrons. High energy electrons. And how do we denote beta particle? We use E of -1 and 0. High energy electrons. They are negatively charged, and that is the reason why they are being deflected to the positive during the experiment in an electric field, and deflected to the north during the experiment through a magnetic field. Their velocity is 2.9 times 10 raised to power 8 meter per second. The charge (1.6 times 10 raised to power 19 coulombs). Here we have 9.1 times 10 raised to power -31 for the mass kilogram. We say this is relatively light. So electrons or beta particles, they are relatively light compared to alpha and gamma rays. So but we have a very strong deflection towards where? In the magnetic field, towards the north pole, isn't it? Towards the north pole. Ionization energy is medium ionization energy. What about penetration power? It's also medium penetration power. Now for the gamma rays that showed no deflection, that was neutral, what do we signify our gamma rays as? They are known as electromagnetic. They are known as electromagnetic waves having a very short wavelength. With a short wavelength. I know how we signify wavelength in physics. Lambda, isn't it? So what else about the gamma rays? Their velocity is giving us the speed of light, which is 3.0 times 10 raised to power 8 meter per second. So this is the speed of light. So imagine a question that says, which of the following particles has the velocity of the speed of light? That is gamma rays. What about the charge? They are electrically neutral. Electrically neutral. They have no charge. So That means no charge. You can see it's obvious from the experiment that their direction of movement remains straight throughout. No deflection was occurred, showing that they have no what? No charge. What about their mass? They what? They have no mass. So I can say that their mass is what? Negligible. What about the effects on the magnetic field? No deflection. No what? Deflection. Because they are neutral. Ionization power, uncle. Little ionization power. But what about penetration power? Very high. Very high penetration what? Power. So in the laboratory, most times, gamma rays is being used because of what? The high penetration what? Power. In fact, for you to stop gamma rays, you need what? A lead block. Despite the fact that a lead block can stop gamma rays, because of the high penetration power of gamma rays, it will still pass through the lead block few centimeters. So most times, when you see someone going to the hospital, for those of you reading medicine, and you want to check how old the person is, those footballers that used to falsify their age, you hear of MIR scan. Because of the penetration power of gamma rays, it will be used to check their bones, the strength of their bones, and then from there they can use half-life to detect their age. Also, what about dead decaying fossils? Come again. My handwriting. Oh, I'm so sorry. Where can't you see? Everything. I can see. Where are you? Okay, because of the distance, Abi. I don't like students sitting at the back. But what can we do? Should I dictate this for you? So where are you now on this table? We are in the first one. So this first place we have the word radiation. Are we there? Underneath radiation we have nature. Underneath nature we have velocity. Underneath velocity we have the charge. After the charge we have mass. Are we there? After mass we have the effects of magnetic field. Then we have ionization power, we have penetration power. So we have the three particles that are emitted during radioactivity: alpha, beta, gamma. Remember in the definition of radioactivity we said these three particles can be emitted, each of them can be emitted, the three of them can also be emitted at once, or two of them emitted at once, together with what? High what? Energy. So on this side of the table, alpha particle denoted with this symbol, and then the nature of alpha particle is a helium nuclei, atomic number 4, mass number 2. The velocity 0.15 minus 0.21. I'm going to leave this table on the board. I'll be making use of this side of the board, so you can always have this table to yourself. So these are the characteristics of these three particles being what? Emitted. So we want to take like a real life situation and see when a radioactive material is undergoing disintegration or decay, and see how these particles can be what? Emitted. So we are going to be looking at some of the equations that are involved. I want to clean this side of the board, please. Aside from this theoretical aspect, the aspect we are heading towards is the calculation, especially when you come to what? Half-life. But I want you guys to know what is going on in case you should see equations on that day. So let's see the types of decay that we can get. So what are we trying to say here? In an alpha decay, the nuclear number, also known as the mass number, decreases by 4, but the number of protons and neutrons decreases by what? By 2. So generally speaking, if we have an element X, for example, element X with what? With mass number or nuclear number A, and then Z atomic number. So now what happens to this element? If this element were to undergo a decay, we are going to have a new element being formed. If it is undergoing an alpha decay, we have a new element being formed such that A is going to what? Lose what? Or decrease by what? 4. So we have A minus 4, while here we have Z minus what? 2. But this shows a release of what? The helium particle, otherwise known as what? Alpha particle. So we're going to have a helium particle here having 4 and what? 2. But when this happens, there's also going to be what? Energy being what? Released. So in this process, Q is the energy being what? Released. So you need to remember this. So whatever equation is given to you, you can always tell which particle or which kind of decay is going on. Yes. Yes. each decreases by 2. The neutron number and the proton number each decreases by what? 2. Because inside of this, we're having 4 minus 2 is what? 2. In an atom, we have neutrons, electrons, and what? Protons. Do you see that? So what we're talking about here, the mass number A decreases by 4. But inside this shell, each of them here decreases by 2. But we can only show one of them here, Z. Can you see that? So here, it's showing that Z minus 2 equals to 2. Do you know that if Z loses 2, the protons also loses what? 2. So this occurs in what? In alpha decay. So a practical example of a radioactive material that what undergoes decay is radon. Radon having a what? Mass number of what? Or atomic number of what? 226 and mass number of what? 8. Look at this. This is decaying to form another element called radon with what? Atomic number 222 and then 80 what? 86. At the same time, you can see that a helium particle and then energy is also what? Given off. This is radon or radium. And then this is what? Radon. Well, we have my what? Alpha particle or helium particle. And then we have my what? Energy. So we have just talked about alpha decay now. Let's go to a practical example for what? For beta particle decay, and see what happens to our atomic number and mass number when a radioactive element is decaying. I want to clean. Oh, sorry. Before a week before your exam, I'm going to do a physics marathon. I'm going to do a physics marathon. That day, I'll teach you for 6 hours. I'll teach you everything for 6 hours. That day is going to be like a soldier going to the warfare. What does he do? He puts on his armor, isn't it? I'll give you the shield, I'll give you the helmet, I'll give you the spear, I'll give you the sword, I'll give you your grenade. I'll arm you. On that day, I will give you more than 200 formulas on that day. On that day, you will know that I am what? Mad. On that day, I will verse. Even when I finish like this, I will clean my sweat like this. I'm finished. I'll be happy going home because I'll go home with a what? Satisfied conscience that my students, they are going to destroy that JAMB. All the tutorials I've been, they usually await that day. They look forward to that day. Do you know why? Because all the things you have forgotten, on that day I'll just be bringing it out. Your eyes will just go, it's true. On that day, I will start from the beginning of that thing they used to teach them in SS1 down to when you finish SS3. I will touch everything. That day when you look at me, you say, this guy is mad. So we are getting towards the end of the syllabus. After this, if we are through with what half-life, decay of a radioactive substance, if we are through, if we are able to calculate it, because many people they find it difficult. This guy has told me before that I should hammer on this very well. Once we are through with this, my revision class has begun. You notice all the things I've been teaching you are all the difficult aspects in what? In physics. Now I will teach you all the sweet what aspects will now be coming from the beginning down to the end in one day. All you need to do for me that day is just be buying pure water for me, bottled water. That's what I just need. No, I don't want 5 alive. I don't want, my own is what? Pure water. Yes. Huh? No, that day I will come normal 8 o'clock in the morning like this, and then I will leave around 6:30. That day I will tell, like I used to tell you, no, listen, I used to tell you, it's not by force. So that day you will bring your food. As I'm teaching, you can be eating. Me, that day, I don't craze that day. I will be giving you points. So take that food self. You no go want eat am. You go the no. You understand? So I want to clean. Can I clean now? Let's go to beta decay and see what happens. Remember, beta particles, they are what? Negatively what? Charged. I should wait small. Oh yeah, now. Many of you have issues with waves. Many of you have issues with lights. I know. Mirror. Some people simple harmonic motion. On that day, I will kill everything. Optics light now. You know when you are reading a very interesting novel, they call that kind of thing a page turner. That's what they call it, page turner. That is to say, every page you read leads you to turn to the other page. That's how it will be, topic by topic. You will be say, give us more, give us more, give us more. On that day, you on your own, you should be able to go away from this place with 200 formulas in your head. Yes, now. The problem we have is that when we see some things, we don't know that we can do it.
We
can do it. You tell yourself that you want to speak French in 3 weeks. You can speak French in 3 weeks if you want to. Do you know why? It's whenever you feed the brain. And the brain has a way of storing information such that the new information you are bringing, it will place it inside what? Compartments. And then you bring an information that you already have, that compartment where the information was before will be what? Highlighted. Can I clean the board? That table, I should still leave it, Abi? Up first. Or I should just still wait small. Oh yeah, now. You're under the sun. Cool. It's not touching. Hello. Pray that you are in that class that day. Pray that you are around. Normal, it will be either on Tuesday or Thursday that I used to come. But if people want it on Saturday, we can also arrange it. Tuesday and Thursday, I do It's okay, no problem. Hello. See, hello. It also depends on you. If I come in the morning, they now say you do not clean, you dirty one place, I will just be looking at you. Me, I'll just be waiting because what is in my head is too much for me to carry. It's anytime you are ready. When you say you are ready, if you are ready by 12 and you know that I'm supposed to use more than 6 hours for you, it's your luck. So that day, if I come 8 o'clock, I'm not even waiting for anybody that is coming. Whether you have seat, you don't have seat, I will start to do what? I will be pouring it out. So if you like, when you come, and they find seat, it's your business. That day you can hang here.
No problem. No problem.
That day you can hang on the ceiling. I don't what? Care. All this I say, sit down, stop that. I will not do that. I will just be talking. Baga, baga, formula, baga. Everywhere will scatter. If you like, if I turn back, like, sit on your neighbor's head. You kilo come. I will do as if you are not there. Go and ask them somewhere. That's what I did for them. All this one I do now. Wait, don't clean the board. Wait, as I dey write that day, I dey clean am. Another one, I dey clean am. This one don't clean the board. How many minutes I'm here now? Can I clean it now? So for bitter decay, so what happens when a bitter particle is undergoing decay? Just as we have seen that it's made up of what? Electrons, isn't it? So this is what happens. So in bitter particle decay, m, which is the mass number, decreases by what? 1. And z increases by 1. So what are we saying? Look at the particle Az of the element x, and z increasing by what? By 1. You can see increasing by 1, but at the same time releasing what? A beta particle what? Emitted. Electron what? Emission. So beta particle decay is also known as what? Electron what? Emission. Electron is what? Being emitted, and alongside what? High what? Energy. So a practical example of a radioactive material undergoing beta particle decay is what? Beryllium. Decaying to form the same element but different what? Mass number. Look at this. So look at an example, a practical what? Example. But if you take note, in the alpha particle, a new element was formed, isn't it? But in this beta particle, a new element was not formed. Instead, what it formed was an isotope of the same what? Element, having different mass number and different what? Having the same atomic number but different what? Mass number. Can you see that? So electron being what? Emitted alongside what? Energy. Now beta particles sometimes can also emit electrons. Those kind of electrons are called positrons. So under beta particle we have two types of emission. This one, electron emission, is what? Giving off. That one, positron. You see that electron now, it will no longer have a negative charge, it will have what? A positive charge. So I want to show you the difference between that one and this one. But both of them are still under what? Beta particle decay. Can I clean the board? Can I clean it? I can clean it now. No, that side. I can clean it now. I can clean it, Abby. Can I clean it? Yes, sir. Yes, sir. So we have another type of beta particle. This same beta particle. Yes. And this one is called positron emission. So here, A is what? Is unchanged. The atomic number is what? Unchanged. But what? But Z decreases. This one is the opposite of the other one. By what? By 1. So look at this. A, Z, an element undergoing what? Positron emission. So Z now is decreasing by what? 1. But look at the electron. Look at the electron that is written here. There is no what? No minus. This type of electron is known as what? Positron. Look at that. In the former one we did, Z was increasing by what? 1. But here, Z is decreasing by what? 1. So we move directly to the what? Gamma decay. The gamma decay is known as gamma radiation what? Decay or gamma radiation emission. So in gamma, the element does not change. This one is very simple. The element does not change. Who can tell me why the element does not change in gamma emission? You are not the plate, it's neutral, isn't it? Nothing concerns it, it will just remain the same. The only thing that happens is that because of the high penetration power, it can move from a lower state to a higher what? State. So generally this is what we have. We have the elements such that atomic number and mass number remains unchanged. But at the same time, energy is also what? Given off. So a practical example of this would be codon 66 and 27 undergoing a gamma decay, giving off gamma particles, the elements remaining unchanged. Codon remains unchanged, 66, 27, and then giving off what? Energy. Question time. There's time for what? Everything. People that are done writing, they are here. They are ready for what? Question time. You are still what? Behind. Imagine if in your house you are still watching black and white television. Will you be happy? Some of you did not know that something like that even existed. Back in the day, if you have that TV, you are a big boy. That one, they used to bring one very big cupboard, they put it there, and they will close it together like this. Then your father will use key and lock it. And then it's only one station that used to show. NTA. NTA will start by 4 o'clock and close by 12 midnight. Anything after this hour, if you on it, you will see white line. People are enjoying now. Everything is there for you now. Anytime you want TV, you will see something to watch. Ah, that time nothing like that. That time no digital TV now. Everything was analog. Hello. Hello, question time. Are you there? Are you there? Example 1. A nuclide. A nuclide. I want to clean. So you guys are done with this table. I can clean this table now. A nuclide. Example 1. A nuclide.